that we computed last time, which give you the anisotropy in temperature that you would observe in one given direction as an integral, and we can simplify this integral in the instantaneous decoupling limit. So an easy application of this formula is if you think of an experiment like the COBE satellite. You have all seen temperature anisotropies mapped by COBE. This was a result of 1992. The first map of CMB anisotropies with blue and red spots corresponding to cold and hot spots, and with a low angular resolution. What does it imply? That the angular resolution is low. COBE, or any CMB experiment, is looking at photons coming from a sphere, our last scattering surface. On this sphere, I can identify a length scale corresponding to the Hubble radius at decoupling. So points which are separated by a larger scales correspond to Fourier modes which were outside the Hubble radius at the time of decoupling. This scale is seen under an angle of approximately 1 degree. And the angular resolution of COBE was of the same order of magnitude. So COBE was only resolving angular separations corresponding to super Hubble modes. Now, on super Hubble modes, we obtained some results last time, namely the adiabatic initial conditions relating delta gamma to delta B to other perturbations. And we can apply this immediately. If you look at super Hubble scales, you can show that the Doppler effect is negligible. The Doppler effect contains a velocity, so it contains a gradient. So it's not important for very large scales. The integrated Sachs-Wolfe effect is small and can be neglected in first approximation. In this case, the temperature anisotropy seen in a given point is just given in the instantaneous decoupling limits by the intrinsic temperature anisotropy on the point you are looking at on the last scattering surface, corrected by the gravitational potential in the same point. Now, let us use our calculation of last time concerning relations between perturbations outside the Hubble radius. This is delta T over T. And because rho gamma is proportional to temperature to the force for a relativistic particle, delta gamma is equal to 4 delta T over T. So this theta 0 can be rewritten as 1/4 of delta gamma plus psi. But we found the relation outside the Hubble radius between delta gamma, baryon, and metric perturbations. Remember that outside the Hubble radius, delta gamma is equal to 4/3 of delta B. And we say that psi is equal to phi. And finally, that minus 2 phi is equal to the dominant density perturbation. Decoupling takes place at the beginning of matter domination. So the dominant perturbation during matter domination is given by delta B. This is what we said at the very beginning of yesterday. So if I recollect this information, I have here a 1/4 of delta gamma can be replaced by 4/3 delta B. Delta B can be replaced by minus 2 phi or psi, it's the same. And then I have a plus psi. So this gives me here a minus 2/3 plus 1 of psi, and this is 1/3 of psi. I saw a typo in the notes, by the way. I inverted this 1 and this 2 in the notes. This result is fun because it tells us something counterintuitive. You see that this second contribution is larger. So here we have the effect of intrinsic temperature, and here we have the effect of gravitational potential. It is the second term which dominates. It means that when I see a positive temperature anisotropy, it corresponds to a positive gravitational potential, so an underdensity. So in the Kobe maps, a hotspot corresponds to an underdensity, and a cold spot to an overdensity. And maybe some of you had the opposite impression. It's because this term has an effect which is opposite to the first one and is a bit larger. Okay, so this closes section 3. And we are starting now with section 4. As I said yesterday, to motivate section 4, this formula is not very useful because we are only interested in the statistical properties of CMB maps. And so the object of interest for us is not the anisotropy in one direction, but the two-point correlation function of the map. So we start with a little bit of formalism. So this is about the spectrum of temperature anisotropies. And as you probably studied sometimes in a basic course of cosmology, delta T over T, the observed temperature fluctuation, is very often expanded in spherical harmonics. So in principle, for an all-sky CMB experiment, an observer can compute the collection of ALMs. And this is nothing but our good old variable theta, computed today at our position. And as we said yesterday, if I see photons in a direction n, it means that they propagate in the direction minus n. I would like to find a relation between ALM and the quantity that we derived from this theta. We have seen that this theta can be first Fourier transformed and then Legendre expanded in multiples theta of L. With a little bit of very simple algebra based on the orthogonality relation of the spherical harmonics, you can show that there is a linear relation between the two. The ALM can be found by integrating with some kernel, by integrating over the multiples theta L, which depend only on T, so it's T0 here, and on K. And this is the direction of K. It's a unit vector, so it's K divided by its modulus. Okay, it's useful to see this linear relation because then we can compute the two-point correlation function of the ALM. These coefficients are complex, so usually the two-point correlation function that people compute is ALM, ALM star, L prime, M prime. If you plug this relation, you work a little bit. You find first that the result is proportional to the Kronecker of delta LL prime, MM prime, times something. This has to do with the fact that in Fourier space, all the two-point correlation functions are proportional to a Dirac of K minus K prime. So it has to do with the statistical homogeneity of the universe, as we mentioned yesterday in Fourier space. So only a coefficient with the same L and M's are correlated. Now, what you find from this formula after a little bit of work is 1 over 2 pi square sum of dk over k times our multiple, our transfer function for the multiple of T0 and k. I don't put here a vector here. It's not a mistake. It's because instead of a mode, I'm looking at a transfer function times the primordial spectrum P of R for curvature. Okay. So it tells us something that we could expect, that this two-point correlation function is given by the primordial spectrum corrected by the square of the transfer function for the photon multiples. And now that we have decomposed the calculation in this way, we see that in order to compute this temperature spectrum in harmonic space, we only need to be given a primordial spectrum by somebody who has studied inflation, and multiply it by this transfer function that we can compute by integrating the Boltzmann equation. I would like to come back on these brackets. It's always a tricky point to understand what these brackets mean. We are talking of a stochastic theory, okay? So these brackets have no meaning related to concrete reality. They mean averaged over many outcomes of the theory. Or you could say over many realizations of our universe given a theory and some two-point correlation functions. And of course, what we see in temperature maps is not an average over many realizations. It's only one realization. And that could be very problematic because if we want to compare theory and observations in this case, it could be as bad as if I propose you the following question. I tell you, I've sorted out a random number. The value I got is 10. What do you infer on the variance of this variable? Okay. That would be a real problem. Why do we escape this problem? Because this quantity depends only on L and not on M. No M dependence. Okay, E and A are different between French and English, so I'm never sure if I should put an E or an A. Is it correct? Yeah, okay. A would be in French. Okay, no M dependence. Why? The fact that this guy doesn't depend on M is related to the statistical isotropy of the universe. And to the fact that the power spectrum in Fourier space depends on modulus but not on direction. Indeed, L is an information about the scale of the fluctuation you are looking at, and M about the orientation of a particular multiple. And of course, the power spectrum should respect the overall rotation invariance and should not depend on M. So in fact, we can measure this spectrum for many ALMs with different M's but the same L. So we can measure many outcomes of the same random number. And indeed, what experimentalists would do in order to measure the CMB spectrum would be to measure the following quantity. The average over the ALMs for all the M's. So you sum over all the M's. There are 2L plus 1 of them, and you take the average. And by doing this average, your result will get closer to the true theoretical variance. The question is, how much closer? You can compute it. You can make the computation of the variance of this CL observed minus the true CL of the theory given by this. Okay, so you take the root mean square, and the theoretical calculation tells you that this dispersion is expected to be equal to 2 over 2L plus 1 CL square. So this is like the square of the theoretical error that you will make if you have an even infinitely good CMB experiment. And it's called cosmic variance. And you see that if you are at high L, you can average over many independent M's realizations, and you will get very close to the right result because the variance will go to 0. But for small L's, large angular scales, you don't have this opportunity, and you have a large theoretical error. So in plots of the CMB, we have this famous spectrum that we will introduce and discuss later on. This is L, and this is this quantity that we call, oh, sorry, I forgot to say what CL was, so maybe you were lost. CL is just the name of the bracket here. CL is just, it's called the temperature power spectrum. Okay, so when you plot this C of L, you expect that the data will be scattered around the theoretical model. And you don't know the theoretical model in advance, of course. And this scattering corresponds to this cosmic variance. So you often see plots with this. The curves are the theoretical curve plus or minus the cosmic variance, which becomes very small. You can understand this in the following way. The theory is good if the experimental points are not exactly on the line, but within this band or not too far from this band. And indeed, when you look at raw data from WMAP or any other experiment, you see very well this large scattering here, and then the scattering becomes invisible by eye. Okay. Yes?
It doesn't depend on time, so you're just looking at the time when the CMB happens.
Yes, we are looking at it today, so we are looking at it like 13 billion years approximately after decoupling. And you are right that this quantity, in principle, evolves with time, because what we see now are photons coming from a given distance. But if we repeat the experience in 10 years, we will see photons coming from a larger distance. So the last scattering surface, strictly speaking, is a quantity depending on time. Now, if we repeat the experience in a few years, of course, the difference compared to 13 billion years is small. So the calculation has been done of how much time we should wait before seeing a significantly different CMB map. And the result is 1 million years. Okay. Other questions? Good. So, as we were saying, at this point, if I give you a computer and the Boltzmann equation, you can integrate them. You can find this theta of L, make the convolution, and predict the C of L. Because there is a set of Boltzmann equations expanded in Legendre space. So it's a complicated system. You have, as we said, a system of coupled differential equation for all the multiples ranging in principle to infinity. So since you cannot make computation up to L equal infinity, you make a truncation scheme. And if you want to compute this quantity, for instance, if you want to compute the C of L until L equals 3000, this is a typical value at which we make observations, you need to integrate at least 3000 equations. Even more if you don't want the truncation to lead to some errors. It is computationally heavy, and if I stop my course here, we will not have gained much physical insight on the meaning of this C of L. So we are going to do one more thing. We are going to use a line-of-sight calculation. Yesterday, we did a line-of-sight calculation. We integrated the Boltzmann equation along a given line of sight in order to derive this formula. This was a line-of-sight approach in real space. We will not do it explicitly because we did it explicitly yesterday, but by taking your time, you could derive a line-of-sight integral in Fourier space. And this is the one that we need in order to compute the C of L. So I give you the result. It's extremely similar to the formula here. Theta of L of eta and k. So it's the transfer function is the integral still over d eta because it's still along the line of sight. So it's not intuitive because line of sight is in real space. We are mixing one line of sight with Fourier space. It's absolutely not intuitive. It's just something you have to do mathematically, and because the mathematics are correct, it must be correct. But don't try to think about what this means. Okay. No, we will be able to give some interpretation, but it's a bit hard. Okay, so here you have again the visibility function times theta 0 plus psi. So there will be a Sachs-Wolfe effect again. There will be again a Doppler term. It takes a slightly different form because we are in Fourier space. This theta b is related to the velocity of baryons. The definition we gave was that theta b is related to the divergence of the velocity. This is why there are some k at the denominator here. Plus the integrated Sachs-Wolfe term. And now this needs to be convolved with a spherical Bessel function. Why do we have spherical Bessel function in the game? Because they are the Legendre coefficients of plane waves. So they appear in the expansion. And between the brackets, we have a function that people usually call the source function of temperature anisotropies. S for source, T for temperature, and it's just like transfer functions. It is actually a transfer function, since it's a linear combination of the other ones. So it's a source transfer function. This result, which is exact, is extremely powerful because it tells you that if you want to compute this quantity, you don't need to actually integrate the Boltzmann equation up to a very high L. You can just relate theta of L at arbitrary high L to theta of 0 plus metric fluctuations plus the baryon velocity. So in practice, in Boltzmann code computing the CMB, this hierarchy of Boltzmann equation is integrated only over very few multiples, because what we really want at the end of the calculation is to have this theta 0 correct. So the truncation can be done at low L. But on top of providing a good framework for calculation, this formula will help us to understand the shape of the CMB spectrum. In order to gain a little bit more insights, one can use, like yesterday, an instantaneous decoupling approximation, treating J as a G as a Dirac function. And one can use also the fact that for high L, this spherical Bessel function is very peaked close to x equal to L. So you can see it almost as a Dirac function, of x minus L. What does it mean? It means that when I compute my theta L, if you look, for instance, at the Sachs-Wolfe term, my theta L will depend mainly on these Sachs-Wolfe terms evaluated at the time of decoupling, because this is when G peaks. But moreover, theta L only gets a contribution from the value of K such that the argument here is equal to L. Okay, so there is a double simplification. And you will see it more clearly if I make a little drawing. Here is the observer looking at the last scattering surface. If I try to compute the spectrum for a given L, CL, it means that I'm looking at a two-point correlation function, and I compare points with an angular separation theta equal to pi over L. Okay? This is a relation between multiples and angles in the harmonic formalism. On this last scattering surface, I see the projection of Fourier modes, perturbations. And when I compare these 2 points, I'm sensitive to Fourier modes with, for instance, a maximum here and a minimum here. Okay? So I'm sensitive to Fourier modes such that this distance here is 1/2 of lambda, and 1/2 of lambda is 1/2 of the scale factor at decoupling times 2 pi over k. So with this little drawing, we are saying that when I look at a multiple L, what I see is a distance on the sky corresponding to these Fourier modes, okay, with the following relation. What is this distance? This distance is the angle here times the angular diameter distance computed up to decoupling. I guess that with Ed Bertschinger last week, you have seen the angular diameter distance, right? There is no massive, yes, approbation. Yes, there is. Okay, you are the massive approbation. Thank you. Okay, so the angular diameter distance gives you is a non-trivial function in cosmology. And of course, if I was in a Euclidean space, I would only use a radius. Okay, so this is this distance, theta times the angular diameter distance to decoupling. Here you could put the redshift or the time or anything. It's the time of decoupling. And this is equal to this quantity, so A at decoupling, pi over K. So there is a one-to-one correspondence between the values of L and the values of K. And it's given by this relation. K is equal to, so this is pi over L. So K is equal to L times A decoupling over dA decoupling. So let me recap. CL is given by roughly, because I'm using in fact a small angle approximation here, is given by the power spectrum of the first term, theta 0 plus psi, which accounts for the Sachs-Wolfe effect. Remember that these are functions of eta and k, evaluated at eta equal eta decoupling, and evaluated at k is equal to L A decoupling over dA decoupling. And this simplification, which is only an approximation, is a result of the instantaneous decoupling approximation and this small angle approximation that I used here. And this, we can try to compute it and understand it easily. And it will give us an idea of the shape of the Caesar L. So this is for the Sachs-Wolfe. There will be also, for the Doppler term here, something related to theta b, the spectrum of theta b, evaluated for the same points and wave number. And here I will try to be qualitative, because you see upstairs there is a j, there is a k square at the denominator, so I should work a little bit more here, but I will give you some qualitative results on this Doppler effect. Well, actually, we can put at least a k square here. And then for the integrated Sachs-Wolfe, the instantaneous decoupling approximation tells you that you should consider this term all the way from yourself to the last scattering surface. So then for the integrated Sachs-Wolfe, you should not evaluate this power spectrum at a given time. You should think that we see the last scattering surface, but the integrated Sachs-Wolfe effect comes from any time between last scattering and you. It comes from, in fact, the fact that this potential fluctuates at low redshift, we will see mainly, and also high redshift, but it fluctuates all along the line of sight. So, in fact, you probe the power spectrum of phi plus psi at all times, but for each given time, you probe a wavelength given by the same reasoning. So it's like schematically an integral over time of the power spectrum of phi prime plus psi prime, this time at any time, and for a corresponding value of k equal to L times A at a given time divided by the angular diameter distance at a given time. So you get the contribution from very small wavelengths close to you and larger wavelengths further away from you. And I would say this gives a rather good qualitative understanding of CMB anisotropies. So now we will be a bit more precise. We will compute roughly the evolution of these different quantities. And finally, we will invoke this formula in order to guess the shape of the scissor well. And we can anticipate a little bit what will be the result, because the physical mechanism which is ongoing is the following. In the very early universe, if we look at perturbation much larger than the Hubble radius, k much smaller than AH, initial conditions fill the universe with inhomogeneities in all species, including photons. Okay, so we have, let me draw only some overdensities of different size. Okay, I draw them as spherical, but of course, you get some very complicated patterns. Now, what happens during the evolution? When a given mode, we will see that when a given mode becomes inside the Hubble radius, then there is a mechanism of diffusion. There is a propagation of a wave front exactly as if there were acoustic waves propagating. It's not an if, in fact. These are acoustic waves. Because we are talking, before decoupling, of a tightly coupled baryon-photon fluid. In this fluid, there is pressure. So it's like in the air. If you put an overpressure, it will propagate. The famous CMB acoustic oscillations are just the acoustic propagation of these overdensities with time. So at a later time, say at decoupling, for instance, each given overdensity has propagated and has created some patterns. And here I simplified so much as to draw dots. So I should draw now some rings. But of course, in reality, there is not this spherical symmetry. But schematically, it gives a fairly good idea of what's going on. So each overdensity has propagated and is now on a ring. And the radius of all these rings is actually the same, because the sound speed has a given value in the fluid. And so you can compute this radius. This radius in comoving space is what we call the comoving sound horizon. And it is the integral between initial time and final time of dt times the sound speed in the fluid, which in principle can be a function of time, divided by the scale factor. So all features have propagating along this distance. The dispersion relation in the fluid is such that one given overdensity will correspond to one wave front. Okay? It's not always the case in nature. On the surface of water, if you put a perturbation, you have several rings propagating. This is due to a very peculiar dispersion relation. Here, this is not the case. There is only one wave front. Now, how can I know if this mechanism is correct? Precisely by computing the two-point correlation function of CMB maps. Because, of course, if I compute this two-point correlation function, I will find a feature when the two-point correlation function corresponds to a distance equal to twice the sound horizon. Because, in fact, when I look at this two-point correlation function, I pick up densities originating from a single initial perturbation. So I pick up a correlation. And this is the whole idea behind the CMB anisotropy statistics. So if you compute the angular correlation function, you could define C of theta as the angular correlation function of delta t over t, meaning that you make the average over all n and n prime such that they are separated by an angle theta. This is a correlation function in angular space. And clearly, it will have a feature for the angle under which we see twice the sound horizon at decoupling. But we did not introduce this two-point correlation function. We introduced CL, which is a harmonic space version. This CL is like the Fourier transform of this one. The Fourier transform with respect to real space, three-dimensional space, is the same as the harmonic transform with respect to angular space. Okay? So going from here to here is like going from real space to Fourier space. So this C of L will have a feature for the L corresponding to pi over theta of the feature of the other guy, plus harmonics, as it would be the case in a Fourier transform. And this is the reason for which we will observe multiple peaks in the CMB. There are multiple peaks, but they refer to a single feature in real space. And this is the reason for which they are exactly spaced equally. The interest of working in harmonic space is that there is a lot of physics contained in this correlation function. We will see that all the little details concerning photon decoupling, coupling with baryons, interactions with gravity, this little detail would affect the shape of the feature in angular space. And so it will affect the relative amplitude of the harmonics in harmonic space. And the difference between two models are more clearly seen in harmonic space. This is why people use the C of L. But in principle, they would be allowed to use the C of theta, which contains the same information. Do we have questions at this point? Okay, so now we will be more specific about the cosmological evolution. Here we did only a bit of geometry, and now we will try to understand how these different transfer functions evolve in the universe. So section 5 will be called acoustic oscillations. So things would be really complicated if we wanted to write an equation taking into account the fact that photons decouple slowly from baryons at recombination. In order to keep the equation simple, we are going to work in the tight coupling approximation. Which is, of course, valid before decoupling. And then I will tell you what are the corrections to be expected when you are more realistic. In this limit, the baryons and the photons can be seen as a single effective fluid. And we can get the equation of propagation of perturbations in this fluid by combining the photon and the baryon equation of motion. We can combine them in order to cancel the coupling term, which is extremely large, of course. And I will give you the results. So first, in this fluid, we have a simple relation between delta gamma and delta B. There is a double motivation for this relation. First, it is verified outside the Hubble radius because of adiabatic initial conditions. Second, it is imposed by thermal equilibrium. I recall you that rho gamma goes like T to the 4, so delta gamma goes like 4 delta T over T, while rho baryon, being non-relativistic, goes like 2 to the 3, so delta B goes like 3 delta T over T. So you see that tight coupling, thermal equilibrium, imposes this relation. At first order in the tight coupling limit, we have also theta gamma equals theta B. We have seen yesterday that the Thomson scattering term tends to align the two fluids, to make them move with a single bulk velocity. Okay, and finally, in our fluid, we can define an effective sound speed for the total fluid. This effective sound speed is given by delta rho gamma plus delta p gamma plus delta pb divided by delta rho gamma plus delta rho b. Baryons being non-relativistic, we can, of course, neglect their pressure. Okay? We know that for relativistic photons, this is 1/3 of delta rho gamma. So if I divide everything by delta rho gamma, I have 1/3 divided by 1 plus delta rho b over delta rho gamma. The last step is to expand delta rho as rho bar times delta, to use this relation between the deltas, and you get 1/3 times 1 plus 4 rho b over 3 rho gamma. And this factor that will play a significant role is usually called R. R is the time-dependent baryon to photon density ratio. This guy goes like a to the minus 3, this one like a to the minus 4. So R grows with time like the scale factor.
Question.
Yes?
The equation of the state of photons is 1/3.
1/3, yes.
But it's not clear for me why the velocity of sound of photons is also 1/3.
Good. It's not difficult to show that if you have a fluid, really a perfect fluid, the sound speed squared must be equal to the equation of state parameter. This is not true in general. It's not true for a scalar field, for instance. But for a fluid, it's always the case. We can see the proof together. It's very simple. We can see this later. Okay. So now, my master equation is theta 0. Remember, this is a monopole. Okay? Prime prime plus HR over 1 plus R theta 0 prime. This starts like a standard equation of diffusion where energy is conserved. Not surprising. No, sorry, I'm mixing up with another equation. No, it's not an equation of diffusion. It starts like the equation of a harmonic oscillator. And you will see that we can push the analogy. Plus k square cs square theta 0 is equal to this times this function of the metric. And to give a quick interpretation of the terms, we can say that this is a damping term, a friction term, and it is related to the baryon density. It's a baryon friction term. When in the very early universe during radiation domination, rho of baryons is much smaller than rho of photons. So we can take this equation in the limit r equal to 0. It gives us, for instance, cs square equal to 1/3. Around the time of equality and close to decoupling, the baryon fraction becomes important. R becomes of order 1. Then this term cannot be neglected, and there is some dissipation in the system. This is an effect of the baryons. The baryons not being relativistic introduce this friction in the medium. This is a term of pressure. Anything multiplying cs square comes, in fact, from a delta P. So this is the pressure force. And we see that if we had a 0, we would have simply a free harmonic oscillator. Okay? So having pressure in the fluid is indeed the condition for having a propagation of acoustic waves. Next, we have some driving forces coming from gravity, since they are metric perturbations. This is simply the gravitational force. Below the Hubble radius, it's simply the force of Newton's gravity, in fact. And this is a dilation effect that we explained a bit yesterday. At leading order in tight coupling, this equation contains all the effects. There are no other approximations here than tight coupling. Suppose that we are in the limits of the early universe of radiation domination when R is much smaller than 1, and we can neglect R. And suppose that we can neglect these other terms, which is the case. Actually, it is a case we will see later when this is true. But it can be true in some limit. Then we have the simple equation theta 0 prime prime plus k square CS being equal to 1/3 theta 0 is equal to 0, and the solution is a simple cosine of k CS eta with a constant in front. Why do I write a cosine and not a sine? Because at early times, this is 0, and I know that delta gamma is a constant. So theta gamma, theta 0 is also a constant. So the adiabatic initial condition pick up the cosine, not the sine. Okay, in this very simplified picture, we would say that as long as a given Fourier mode is on scales larger than the sound horizon, then this is smaller than 1. For lambda, much larger than the sound horizon. Going from this inequality to KCS eta smaller than 1 is very easy if you take the expression of the sound horizon. So in this case, for causality reason, everything is frozen. When lambda is instead smaller than the sound horizon, then inside the fluid you have a propagation of acoustic waves, which corresponds to oscillations in Fourier space. Now we are going to refine a bit this picture by taking into account the effect of these coefficients. This is necessary in order to understand the detailed shape of the scissor wave. Yes, sure.
In the latent effect, we now have the second derivative of phi.
Yeah.
Where did that come from?
Yes, so the dilation effect that we wrote yesterday had only one derivative in this, yes. It comes from the fact that you take, implicitly you have to take the derivative of the geodesic equation in order to reach this. So there is like one more derivative with respect to yesterday. As I said, you obtain this equation by combining the continuity and Euler equation of baryons and photons. And in order to do this combination, you have at some point to take one derivative, and this leads to this phi prime prime. Okay. Other questions? Okay, so now we will do a plot summarizing all the CMB physics, more or less. Well, this is a bit too much, but a lot of it. At the end of the course today, I will show you some numerically computed spectra, if I have time. Otherwise, I will do it at the beginning of tomorrow's lecture. Okay, so we plot time going from up to down, and we plot Fourier modes. We have this characteristic line corresponding to Hubble radius crossing. So this is when K equal AH. Now, what are the characteristic times in the problem? There is a time of equality between matter and radiation. This is also the time when R becomes of order 1. So this is radiation, matter, equality. Soon after, there is a time of photon decoupling. How do we know that it takes place after? I don't know if Ed did the calculation or not. It is simple to see that for the allowed values of cosmological parameter indicated by a CMB, the redshift of equality is of the order of 10,000, while the redshift of decoupling of the order of 1,000. So decoupling takes place at the beginning of matter domination, not at the end of radiation domination. Okay, the other time is today. There is another characteristic scale in the problem. It's when lambda is equal to the sound horizon. This can be rephrased as K CS eta of order 1. So there is a line of Hubble crossing, but there is also a line of sound horizon crossing. During radiation domination, because CS square is 1/3, the Hubble radius and the sound horizon are the same up to a square root of 3. So my sound horizon crossing line is here, is parallel, it's just a bit smaller. And then after equality, R becomes important, the sound speed drops to 0, and this will asymptotically be vertical. So this is sound horizon crossing. We know that perturbations are frozen outside the Hubble radius with the adiabatic initial condition constraints. There is no time evolution. If you want to be very picky, we said yesterday that there is just a small evolution of the metric fluctuation at the time of equality because the equation of state of the universe is changing. But if you are not a specialist, you can forget this. But in each of these regions, the perturbations are frozen. I'm going to argue in very simple words that there is a region here that I will call 1, in which the oscillations are driven. So a regime of driven oscillations. And then we will see other regions. So about this driving, the point is that when you enter the sound horizon, not only the mode wants to oscillate, but they also feel the driving term on the right-hand side. They don't feel it before, because before, outside the Hubble radius, you can neglect the k-square, the gradient, and phi is static. But when you come into the Hubble radius and you cross the sound horizon, phi and psi are not static anymore, the gradient is large, and gravity is important. So the gravitational terms have two impacts. They enhance the amplitude of the perturbation of the oscillations of theta 0, and they shift the 0 points of oscillations. And the second one is easy to show in one line. If I want to know the 0 point of oscillation, I look at this equation with no derivatives on the left. So I get that k square cs square theta 0 is equal to, now on the right-hand side, the leading term is usually the first one. So I keep only minus k square over 2. It's a 3, actually. That was a typo. It's a 3. So k square over 3 of psi. Okay, and now I can simplify by k square. I replace ca square by the values that we wrote, and I get that theta 0 equilibrium is equal to minus 1 plus r psi. This is the 0 point of oscillation around which you oscillate. And we see that this 0 point of oscillation depends on baryons. If the baryon fraction increases, you shift this 0 point. This will be very important later. This driven oscillation regime is only around the time of sound horizon crossing, because when you are in this region, well inside the sound horizon, the metric perturbation decay very quickly. Phi and psi become very quickly negligible. I want to speed up a bit, but you could show it with the Poisson equation. Well, no, actually, we should not hide these kind of things. The Poisson equation tells you that k square psi goes like delta gamma, with some factors here, but not depending on k. So if delta gamma has oscillation of roughly constant amplitude, it means that psi has oscillation of amplitude decreasing like k square. Sorry, there is an AH here. If you write the Poisson equation and use the Friedman equation, you have an AH square here. So psi goes like AH over k square delta gamma. And it means that if delta H has constant oscillations, psi has suppressed oscillation because this factor is decreasing. So when you are in this region, the oscillations are not driven anymore. You can drop the term from gravity. The interpretation is that this region is the only one in which CMB perturbation fills species coupled only gravitationally to photons. So later we will discuss the effect of cold dark matter, for instance. The only region where cold dark matter would have a chance of impacting directly the CMB would be this region through gravitational couplings. Otherwise, the fluid does not feel gravity. What happens physically inside the sound horizon is that pressure forces become much more important than gravity forces. Okay, then when you arrive in the region 2, so a mode here evolves vertically. It is frozen, then it feels driven oscillation, then it arrives in region 2, and in this region we have constant oscillations. Or if you want, well, maybe stationary is a nicer word. Stationary oscillations. Why? Because we are exactly in the conditions that we described before. We are in the radiation-dominated phase, so we can neglect R. Gravity driving became unimportant, so we have the simple equations that we wrote before with the cosine solution. But this will not be true in region 3, when we are between equality and decoupling and below the sound horizon. Because in region 3, we cannot neglect anymore R. The presence of baryons will switch on a friction term, a decay of the sound speed to 0, and these two items lead to a decrease in the amplitude of oscillation. And also this will lead to an important effect in the CMB spectrum, decreasing of the oscillations due to R growing. Okay. The last subtlety is that we have written everything in the tight coupling approximation. What happens if we try to be more exact? We computed yesterday the diffusion scale in the baryon-photon fluid. Okay. this diffusion scale increases with time. It starts from 0. We say it's initially 0. Today, it's the radius of the observable universe. But around the time of decoupling, it starts to grow quite abruptly. All scales below the diffusion scale have a loss of coherence of temperature because everything gets mixed up by the free diffusion. So all fluctuation below the diffusion damping scale are erased. We could draw a third line corresponding to the diffusion scale. The diffusion scale becomes important only very close to decoupling because it's 0 in the tight coupling regime. So it looks something like this, but then it grows very, very fast. So this is the diffusion length crossing line. And so there is a regime 4 in which fluctuations are very quickly damped by diffusion. Actually, you can show that this introduces an exponential cutoff in the Fourier spectrum of theta of this form, where this wave number kd is a wave number that you can build out of the diffusion length. Okay, and after decoupling, the photons are just decoupled and free streaming. Okay, this is a lot of information, but when we recollect all this, we can understand now all the details and the parameter effects in the CMB anisotropies. And if I... Sorry?
Is the false term called superdamping effect?
Yes, this is also called silk damping, although Joe Silk historically studied this effect for the baryons. But very often the word silk damping is also applied to the photon perturbations that we see here. But it's this, yes. Okay. So now we will make some nice drawing. It will not be very tiring. At least for you. So we will summarize all this information on little plots. And I had to take a decision. Should I show these plots from a numerical computation, like the exact ones, or should I draw them? I think it's more pedagogical to draw them because you can emphasize what you want. But I swear you that I can do these plots numerically, and they look qualitatively the same. Okay, in this plot, we are going to show transfer functions at decoupling. Because we said before that the CMB spectrum is related to the Fourier spectrum at decoupling of theta plus psi for Sachs-Wolfe, theta b for Doppler. This is the quantity that I want to show. Then we will take the square of these transfer functions, and we will get a qualitative spectrum. So first, I will show this theta 0. We normalize the transfer function to the curvature perturbation. A positive curvature perturbation corresponds to a negative theta 0. So my transfer function on large scales is negative. So this is k. This is wave number. The characteristic scale in the problem is the value of k corresponding to the Hubble radius, or more better, to the sound horizon at decoupling. So this value is the one such that k Cs eta at decoupling is equal to 1. It is a value when you start to get some non-trivial evolution. You see that we are plotting the transfer function for all k at a given time. So we are studying this cut in this drawing. So for small k, we look at modes which are still frozen and outside the sound horizon. So then psi 0 had no evolution. It is still given by the adiabatic initial condition. Now we reach the sound horizon. And for the sound horizon, the modes which arrive here started to experience this gravity driving force. And this enhances the fluctuations. So we have a peak like this. On smaller scales, I should start to see the oscillatory patterns with different phases because the mode enter into the sound horizon at different time. So they have time to oscillate for half a period, 1.5, 2 periods, etc. So I will see here the sequence of oscillations. Are these oscillations centered around 0? No, because we computed the 0 point of oscillation. It's -1 plus r psi. It corresponds to a line that I draw here. And around this line, I have some oscillations. I draw in log k. It's more clear because in log k you see better this plateau here. This is why my oscillation look like squeezed. Okay, so this line is -1 plus r psi, and it goes to 0 because inside the sound horizon the metric fluctuations decay. Moreover, these fluctuations are damped by diffusion damping. So now I should correct this plot, kind of thing you can do only on the blackboard, and shows that the envelope of this perturbation is decreasing very quickly. So this envelope is given by diffusion damping. Okay. Next, I can show you qualitatively the behavior of phi and psi, which are equal to each other. They have opposite sign because a negative theta 0 corresponds to an under pressure. An under pressure corresponds to a maximum of the gravitational potential. So it starts from a positive value. So this is phi or psi. Outside the sound horizon, phi and psi are frozen. These two are related by adiabatic initial condition. And inside the sound horizon, this decays very quickly. Okay? Now we can understand what will be the Sachs-Wolfe contribution to the power spectrum. What we need to plot first is the Fourier spectrum theta 0 plus psi, so squared, at decoupling. This will give us the Sachs-Wolfe contribution to the CMB spectrum. So you take the sum of these two and you square. And if you do it carefully, and in fact I copied the solution from the numerical solution, you get a plateau. Then you go to 0 because there is a time at which the sum of these two goes through 0. So it goes to 0, and then there is a first peak corresponding to this scale. The second peak is obtained by squaring this, but you see that the distance here is much bigger than here, essentially because you have shifted the 0 point of oscillations. So this square will give you a small peak. This square will give you again a large peak, but smaller than the previous one. And you will have a series like this, in which you have the envelope given by diffusion, and the ratio between odd and even peaks given by this shift in the 0 point. So in fact, when this curve goes to 0, there is no shift anymore. After a while, the peak becomes like this. Okay, this is one of the contributions to the CMB spectrum. The other important contribution comes from the Doppler effect. The Doppler effect is related to this spectrum, as we said before, at decoupling. Now, theta b is related to theta gamma in the tight coupling approximation, and theta gamma is related to the time derivative of delta gamma. So in fact, the Doppler effect is related to the time derivative of this variable. And this is simple. In a harmonic oscillator, if position goes like a cosine, velocity goes like a sine. So for the velocity, I will find some oscillation centered on 0 and out of phase with those oscillations. So they will look like this. Okay, and I try to put them always out of phase. And there is also diffusion damping here. So this is a transfer function of theta b over k squared. And the Doppler term will come from the square of this quantity. The square appears in the Fourier spectrum. So I have to take a contribution like this. And if I sum up these two curves, I get my approximation for the CMB spectrum coming from Sachs-Wolfe and Doppler. I have neglected so far integrated Sachs-Wolfe. And it has a shape like this. Okay, and the idea, as we said before, is that this is in Fourier space, but there is a one-to-one correspondence in good approximation between Fourier space and harmonic space. So this gives us an idea of the shape of the harmonic spectrum, CL. If you want to be picky, but forget it if you are not specialists, this has to be compared with L square CL. It's a small detail. It comes from the fact that when we did the Legendre transformation, there was a coefficient L plus 1 at some point, whatever. What corresponds to this Fourier spectrum is L square C of L. Okay? And I take just 5 minutes to tell you what we have missed. We have missed two things so far, and then we are done. We have missed the integrated Sachs-Wolfe effect and the reionization effect. And I will show this now in 5 minutes. Yes. So what we are doing looks very sketchy, but you will see tomorrow it is sufficient for understanding exactly what is the effect of each of the lambda CDM parameters on the spectrum. And every little detail of what we said will have a consequence. This shift of the 0 point, this decreasing oscillation, etc. Okay, so we have missed the integrated Sachs-Wolfe term, which comes from phi prime plus psi prime at any time between decoupling and us. So when is phi prime plus psi prime different from 0? Certainly not for super Hubble scales. On super Hubble scales, which we have seen that during radiation domination or during matter domination on super Hubble scales, these quantities are static. A non-trivial result that I anticipate over the lecture of tomorrow on the matter power spectrum. Tomorrow we will finish the CMB and start the matter power spectrum, is that they cannot vary, not deep inside matter domination. During the matter-dominated regime, it's trivial to show that phi and psi are also static, even inside the Hubble radius. So what remains? We can draw it here. As usual, we have eta, we have k, we have Hubble crossing, equality, decoupling. This is radiation matter equality. Then I'm going to show also matter lambda equality if we are in a lambda CDM model, and today. And I'm going to highlight the regions in which the metric fluctuations are non-static. So this very little picky detail that we mentioned yesterday and has almost no consequence is that they vary a bit at the time of equality between the total equation of state of the universe is changing. But this doesn't matter for us. We have seen that phi and psi decay inside the Hubble radius during radiation domination. So here there is a fast decay of phi and psi. The point is that it does not stop abruptly at equality. Phi and psi then will stabilize towards a constant asymptote during matter domination. But it takes some time. And so I will put here some hatches to show that phi and psi are here in a phase of stabilization. Now, at recent time, when lambda becomes important, again, the total equation of state of the universe changes. It goes from 0 to -1. And the story of the equation of state of the universe is important because, as I mentioned, when it changes, phi and psi change also. And so there is a decay of metric fluctuations in this region. Okay? So the CMB will pick up contribution from the integrated Sachs-Wolfe effect coming from two regions. First, when photons decouple, so if we think of integrated Sachs-Wolfe effect, we think of effects on the line of sight of the photon between decoupling and us. So it would be absurd to think about the integrated Sachs-Wolfe effect before decoupling. There is no, okay? So we start thinking on this line. Here, the metric fluctuations are not completely stabilized. So there will be an early integrated Sachs-Wolfe effect. Early integrated Sachs-Wolfe. This effect is not effective for very large scales because there the metric is frozen. It is suppressed by some geometrical term in the other limit. So in fact, it peaks around the first peak, and it can enhance the first peak very significantly. This is the early integrated Sachs-Wolfe contribution. The second region is lambda domination. Here, the metric fluctuation is decaying on all scales, so you could expect to see an effect on all scales. But again, because of some gradient in the equations that I don't have time to show, the effect is enhanced on the larger scales, smaller k. So the late integrated Sachs-Wolfe effect is in fact visible on those scales here. Late integrated Sachs-Wolfe, and it comes from this region. Without this effect here, we would have a plateau reflecting just the primordial spectrum. If the primordial spectrum is exactly scale invariant, then this plateau in L square C of L would be exactly flat. It is called the Sachs-Wolfe plateau. So the late integrated Sachs-Wolfe effect tilts the Sachs-Wolfe plateau. And finally, qualitatively, in two words, effect of reionization. Reionization is an effect taking place at late time, at the time of star formation. Star form at a redshift of 10 or so. So this is before the onset of lambda domination, which is at a redshift of 1. So in this region, my photons have a chance to rescatter instead of being completely free streaming between decoupling and the observer. Fortunately, it's only a very small fraction of the photons which are rescattered. Otherwise, the CMB fluctuation would be completely hidden by some fog. Here, the fog is very light. Only a fraction of the photons are rescattered. And of course, this rescattering just tends to erase CMB anisotropies because of this rescattering, when you look in a given direction, most of your photons come from a point on the last scattering surface with a given value of temperature, but a small fraction of the photons, in fact, have rescattered, and they come from random directions, many random directions, and they pick up completely different values of temperature, which average out to 0. So this rescattered photon partially erase the CMB spectrum, the correlations in the CMB spectrum. And so it will just decrease the amplitude. It's extremely trivial. It's just an amplitude effect. Okay, so the true spectrum is suppressed by a factor which does not depend on L. But this mechanism cannot happen on scales that were outside the Hubble scale at the time of star formation for causality reasons. So there is a range of scales which is not affected. The spectrum is still like this. Then there is a break, and then you have this suppression. Okay, here we have seen the sum of all the effects contributing to the C of L. But at this point, you should be still a bit confused. It is normal, because there are so many things. What we will do in the first half of the course tomorrow is to put some order in this. We will recap one by one what are the effects controlling this shape. We will relate this effect to the cosmological parameter of the lambda CDM model, and we will show on the computer a few plots to see that this is real and that I'm not trying to cheat you. Okay, so we stop here, and so tomorrow we finish the CMB, and we start the matter power spectrum, which is much simpler. Thank you.